Welcome to my presentation. Hello everybody. The title of my presentation is Power Allocation in Sensor Networks for Surveilling Security Zones. I want to give you a short overview about my work. And this is a joint work with my student, Ms. Denise Cappel. And we are from the RWTH University located in Aachen, Germany. So I want to introduce the framework of our application first. We have here two countries, A and B, and in between there's a border, and this white border is divided in many sections, and each section has this structure. We have on the left and on the right side a guard area, which is where the width of this guard area or each guard area is about 10 meters. And between two guard areas, we have an area with a width of some kilometers, usually 3. And what we want to do is we want to localize and to detect or even to classify some targets which wants to cross this border from A to B or A to E. So, and therefore we are using a sensor network, a huge sensor network, and this the sensors of this sensor network are randomly distributed on this area. They are shown in by these circles. The empty ones are sensors which are in sleep mode at the moment. The green ones and the red ones are active sensor nodes, and for example, the green ones are transmitters and the red ones are the receivers. So, and in order to ensure for a good coverage, we have to connect the left side with the right side by chains of radar coverage regions. So what we want to do is we want to have, or we want to maximize the lifetime of such sensor network by the aid of sensor selection or optimizing the power of each sensor node. So what is our goal? Yeah, we want to see which sensor node must operate in sleep mode or must be active, and the challenge is to identify the sensor nodes which are operating as transmitter or receiver. Okay, the first question is which radar system is proper for this task, and we can distinguish between monostatic and bistatic radars. What is the difference? By a monostatic radar, the transmitter and receiver are located at the same position. Therefore, the coverage region of such a radar system is usually described by a circle. So, in contrast, if we have a bistatic radar, the transmitter and receiver are located at different positions, and therefore the coverage region is, in comparison to a monostatic radar, longer, and it is more, it is better than the monostatic radar for our task. So, and the distance between the transmitter and the receiver describes the shape of our coverage region. If we now increase the distance between the transmitter and receiver, you can see we have a different coverage region. And in the case that the power of the transmission is limited, it means that coverage region is, or the distance between transmitter and receiver is also limited. Why? Because we don't want to have disconnected coverage regions. You can imagine if we increase the distance between transmitter and receiver, then we will obtain two disconnected coverage regions, and we don't want to have this kind of coverage region. Okay, what can we do? In general, the coverage region of this radar system, bistatic radar systems, is described or surrounded by Cassini curves, and our task is to overlap such sensor systems as shown here in order to connect the left and the right guard area together. So we want to have such chains or such parts of coverage regions. Okay, and the main question is, for a specific scenario, how many disjoint parts can we find? So what are disjoint parts, or what is the difference between disjoint and not disjoint? You can see here 3 disjoint parts. Disjoint means these parts have no overlapping coverage regions. They have no intersection. So, and we are interested in the maximum number of such parts for a given scenario. So, what we can do to calculate this number, it is a very hard task because it is a combinatorial problem and there is no analytical solution or closed form solution available. And what we have done in our paper is we used a graph-based method to find this maximum number. So here's an example. We can take such radar systems and define the vertices of this graph, and an edge exists between two radar systems if there is an overlapping area. So, and we have the left and the right guard areas also in this graph, and we want to connect the left and right side area through the by the aid of this chain. So you can simply see we have here 9 coverage parts, but there is only 2 disjoint parts included. It is not easy to find them because we have here radar systems which are which consist of the same sensors, and we don't want to have jointly used sensor nodes. So what can we do to find this maximum number of disjoint parts? Well, we can use Menger's theorem. What does it mean? This theorem tells us we have to find the maximum flow in a graph in order to find the maximum number of disjoint parts. So this is very easy for us because we have already described our problem by a graph, and therefore we can calculate this number m. And the problem is now m is not equivalent or not equal to the lifetime of the sensor node. What we need is a ratio which is described by P budget divided by either PT or PR. P budget is the energy of a single sensor node. Let's say it is the battery of this sensor node. And PT and PR are the powers consumed in transmit or in receive mode. And this ratio gives you the amount of cycles for the lifetime of this sensor network. And the multiplication of these two values gives us an upper bound for the unknown lifetime. So this upper bound is very, very sharp. We can see it later in our simulation results, but we are also interested in a simple approximation, which is given here. Instead of calculating the minimum function of both powers, we can replace it by the expected value, and then we have a possible lifetime of the sensor network. So, as mentioned before, this lifetime L star is very hard to calculate. We have also a contribution of finding L star in our paper, but it is only a suboptimal solution. So let's have a look at our simulation results. We are now looking at a scenario which is 1 by 1. The width of the guard area is very narrow. It is 0.025. P-budget, the energy of each sensor node at the beginning is described by 10, and in receive mode, they are consuming a power equal to 0.5. And we are considering two cases, case 1 and case 2, here by these two figures. In case 1, the transmission power is 1, and in case 2, it is equal to 2. So, okay, let's have a look here in this figure. We have here the lifetime, and here the number of sensor nodes in this specific scenario. And in red, you can see the upper bounds, which are proposed in our paper. In black, you can see the suboptimal solutions obtained numerically. And also in blue, the possible lifetime is depicted. And now we can look at the first result. We have here 100 sensor nodes included in this area, and the lifetime of this sensor network is equal to 0. Why? Because we can't find any disjoint part which connects the left and right guard area. Okay, what is the problem? The problem is that the sensor nodes are far away from each other. Okay, we can now freeze this scenario and add more sensor nodes to the same scenario by 100 sensor nodes. And then we see, okay, we can find disjoint path, and the red point shows that the upper bound for this scenario is 100 cycles. The suboptimal solution is about 75, and the approximation is about 70. So we see how close the bounds are, and the real value is in between the black point and the red point. Okay, step by step, we can increase the number of sensor nodes in the same scenario, and you can see the sharpness of our bounds and our approach. In the second scenario, we have only a power which is double the transmission power, and you can see similar results. They are really similar. But as you can see, the distance between the possible lifetime and the upper bound increases in this case. So our result is the upper bound is a good upper bound. The possible lifetime is usually a lower bound, as you can see here, and L star, which is the optimum lifetime, is between the optimal, suboptimal solution and the upper bound. Okay, what is our conclusion in our paper? We have formulated this hard coverage problem as an optimization problem, and we have deduced an upper bound on and an approximation of the lifetime. These are our two main contributions. Thank you very much.